Okay, guys, so we are on the section 9-4 part of the test review for chapter 9. So again, these problems are worth 2 bonus points if turned in by Monday, the first day of finals week. So 9-4 was about the matched pairs or paired data. So we end up with two samples that have some sort of relationship for each of their values. Okay, so number 3 says, fall temperatures in St. Louis seem to fluctuate tremendously, which we all know, but this past fall seemed cooler than the last. I happened to get married this last fall, so I was definitely paying attention to that. A weather analyst selected a simple random sample of 9 fall days. And recorded the 2018 and 2019 temperatures for the St. Louis, 2018 and 2019 temperatures in St. Louis for each of the days. Okay, so our simple random sample was the 9 dates, and then they looked at the temperature in 2018 and the temperature in 2019 for each of those dates. Now, I didn't include what the actual dates were. I just said day 1 through 9, but they were randomly selected. Okay, so in 2018, here were the temperatures for each of those days. In 2019, here are the temperatures for each of those days. We could go ahead and enter this data into Statistics. So in columns 1 and 2, I have entered the data there. But it will also be helpful for us to have the differences between them. So I went ahead and started subtracting. 90 minus 91 is -1, 91 minus 75 is 16, on and on. I left this one for us to do 84 minus 93. Let's just make sure. 84 minus 93. You get -9. Okay, makes sense. So you need to fill in the rest of that chart. Again, I just subtracted 2018 minus 2019, just because 2018 came first. And then I went ahead and entered that column, their actual differences, in column 3. Okay, so it says let mu diff equal the population mean difference in fall temperatures of 2018 and 2019. And again, I know I'm subtracting 2018 minus 2019. So first it says make a dot plot of those differences in temperature for each day. So I have them, there are 9 values. I could make the dot plot by hand, right? I think that's pretty reasonable. So I'm gonna sketch that out pretty quick. All right, let's see, the lowest value appears to be -9. So I'm gonna say maybe this is -10. And the largest value is 22. So I want my dot plot to go all the way out to, say, 25. So let's go -10, -5, 0. I'm trying to make these evenly scaled, but since it's by hand, it doesn't have to be perfect. 10, 15, 20, and 25. Okay, so those are my difference in temps. Okay, these aren't the actual temperatures, these are differences in temperatures. So the first one is -9, so maybe it's right about here. Then -1, 16, 5. So I don't think I actually have any duplicate values, so that's going to make this a little bit more complicated. Instead of separating them out, I'm going to group them together by the closest 5. So -9's closest 5 to the left is -10. -1's closest 5 to the left is actually -5. 16's 5 value to the left is 15. And then 5, another 15, 22, its closest would be 20. 13's closest would be 10, 15, and 11. Its closest would be 10. Okay, so I'm looking at this shape real quick here. It does look kind of skewed to the left, but there are so few values, it's not a very strong skew, and the separation is not very large. So this is not a strong skew. So no strong skew. And it does not appear that there are any extreme outliers. Why am I thinking about that? Because I'm going to have to check the normal condition if I move on to do a hypothesis test. So, of course, part B says, is there convincing evidence that fall 2018 had higher temperatures? They're giving me a hint for my alternative hypothesis. So I had higher temperatures than fall 2019 at the alpha equals 0.01 significance level. Okay, let's get started by stating. So instead of having mu1 minus mu2 here, I have the difference, mu diff is equal to, now it's given to me right there, the population mean difference in fall temperatures of 2018 and 2019. So instead of saying population, one other way to say that is to say the true mean difference in fall temp. I'm going to abbreviate, and I'm going to write the way that I'm subtracting to make it really clear. 2018 minus 2019. All right, now I need my statistic. So this is not x bar 1 minus x bar 2 like it was last time. First sample mean minus second sample mean. This is going to be x bar sub diff, or just sub d, depending on what notation you're using on. So this is the mean of the differences, which is why I went ahead and entered my differences here in column 3. I'm going to find their mean by going to data, explore the data, and choosing column 3. That's where those differences are, and then click evaluate. And it tells me the mean right there, 9.666667. So I think we can round to 9.67. Okay, that's my statistic. I need to know my significance level, which was 0.01, and then I need my hypotheses. So the null hypothesis is always the equality. The difference, the true mean difference is equal to 0, right? The null is that they are not different, that they are the same. So then my alternative, all right, let's see, the mu sub diff, again, is the difference between 2018 and 2019, and I want to know if I have convincing evidence that fall 2018 had higher temperatures than fall 2019. So 2018 would be greater than 2019. And since I'm subtracting 2018 minus 2019, if 2018 is larger than 2019, then this is a positive difference. So my alternative is going to be that mu diff is greater than 0, positive. Okay, so now I need to plan. This is a 2, I do have 2 samples, but they are matched. So really I just have 1 sample where I calculate the difference in temperature. So this is actually a 1 sample. Let's see, it's for mean, so t-test for mu diff. You have to be careful. Whenever you have 2 independent samples, we say a 2-sample t-test for mu1 minus mu2. But we don't have independent samples. We have matched pairs or paired data. So we say 1 sample of the paired data t-test for the true mean difference. Okay, so then we have to check that we have random samples. And it says they collected a simple random sample. So SRS, that's good. And paired data. We don't want it to be independent this time. We want it to be paired data. So then we need to think about the 10% condition. Now we just have really 1 sample here again, the same dates for both 2018 and 2019. So n is equal to, let's see, what did I say, 9. Is that less than 1/10 of all fall days? Well, I could technically calculate that fall is from September, like 20th or 22nd to December 20th or 22nd, something like that. But really, it's about 3 months, which is a little over 90 days. 10 times 9 is 90. So 9 is less than that 90 days or 3 months of fall. So this is met. All right. And then the third condition is the normal condition. Now, I could see if the population distribution is approximately normal, but it does not say that. So then I could check the CLT. I could check that n is greater than or equal to 30, but that's not the case either. N is less than 30. So I'm going to make this really clear. You don't have to write this, but I'm just trying to show you. N is equal to 9, which is less than 30. So CLT doesn't apply. This is the only time that we then go ahead and check the sample distribution. And of course, we just sketched it. The sample distribution above, right up here, shows no strong skew or outliers. Now, I know some of you are probably thinking, again, this does look skewed, but this is a really loose condition. It has to look terrible, just like really, really, really bad skew in order for this condition to not be met. So that condition is met. All right, now we're ready to do. And again, we're going to use StatDisk to get our p-value. So let's go ahead and use StatDisk. Okay, I still have that data entered, and from my notes from last time, I know I go to analysis. Come on, there we go. Analysis, hypothesis testing, and this is where it gets a little bit confusing, I know, because you have two options. We have the data, the individual samples, but we also have their differences entered now. So we could choose mean matched pairs. Make sure our alternative hypothesis is correct. We think the first mean is greater than the second mean. So the mean of the, I'm sorry, I shouldn't have said it that way. We think that 2018 is going to be hotter than 2019 or warmer, have higher temperatures. So we think that difference between them, the true mean differences, are greater than 0. So true mean difference greater than 0 is what we want to select. Our significance level it said to use was 0.01. And then it asked me which columns of data. So I could compare column 1 and column 2, because if I show my sample editor up here, again, that's the 2018 temperature and the 2019 temperature. If I evaluate, let's see, I get over here a p-value of 0.0085. Okay, that's one way to do it. 0.0085. And if you have the actual data given to you, that is a great option for mean matched pairs. But sometimes they don't actually give us the data. They just give us the summary statistics. So if that's the case, we treat this as, go to analysis, hypothesis testing, and we treat it as just one sample. And then we use the descriptive statistics for the differences. So we are going to say that our population mean is greater than the claimed mean, significance level of 0.01, claimed mean is 0. We don't know the population standard deviation. Our sample size is n. Our sample mean, oh, I forget what our sample mean was. It was 9.67. And if I wanted to finish this out, I actually would need the sample standard deviation, and I kind of forgot what that is. So I could go back to my data, explore descriptive statistics for column 3. Okay, I got that mean again was 9.67. The standard deviation, it says, is 9.6566. Also, I'm going to use the full value here for my mean in order to get more accurate information. So I'm going to copy and paste the standard deviation as well. Let's see if I can go back. What does it do? But doesn't want to let me go back. Okay, so I'll have to go to analysis, hypothesis testing, and mean one sample again, and enter all my information again. Population mean is greater than claimed mean. Significance level is 0.01. Claimed mean is 0. The true mean difference I'm claiming as my null is 0. Don't know the population standard deviation. Sample size 9. 9.6667 was my sample mean that I just looked at, and the sample standard deviation I looked at, I'm copying and pasting in. There it was. I think I had one more extra 6 in here. They're rounded to the same decimal place. Okay, so I'm ready to hit evaluate. And look at that, I get a p-value of 0.0085. So either way you do this, whether you actually have the data and you use the hypothesis testing for mean matched pairs, or if you just have the descriptive statistics and you use hypothesis test for mean one sample and plug in the sample mean and sample standard deviation for the differences again, you're going to get the same p-value of 0.0085. Okay, so let's conclude based on that p-value. So let's see, since our p-value equal to 0.0085, it's close, but that is less than alpha equal to 0.01. Now, whenever our p-value is less than alpha, we reject the null. This is the first time we've been able to do that in this review. So we reject the null. That means we do have convincing evidence against the null or for the alternative. But instead of just writing that out in context, I'm going to go back up and check my problem statement. We do have convincing evidence that fall fall 2018 had higher temperatures. I'm going to say had higher temps than fall 2019. There we go. Okay. So then part C says construct and interpret a 98% confidence interval for the mean difference in fall temperatures of 2018 and 2019. So I purposefully chose the significance level to be different this time, for it to be alpha equals 0.01, so that I could show you that a one-sided test, right, where I have either greater than or less than as my alternative hypothesis, and a significance level of 0.01 corresponds to a 98% confidence interval. And again, that would be this 0.01 is all on, in this case, the right tail, which means it would be mirrored to have another 0.01 on the left tail, leaving 0.98 in the middle. So 98% confidence interval. Okay, so let's get started. We need to state, let's see, the parameter was stated above, but we want to say with 98% confidence. And then the conditions were checked above, but we have a different test name. Now we have, again, a one sample, because we're thinking about the differences, one sample T, because it's for means, but this time interval for mu sub diff. All right, now I'm ready for the do step, and again, I'm going to use StatDisk. Okay, so it's tempting to just come up here and use this confidence interval, and I think that's what I'm going to do. But I will still check and make sure if I plug in 98% everything, it works out. So confidence interval of 0.34337 to 18.98997. So let's write that down. 0.34337 to 18.98997. All right, so let's check that using the confidence interval method. So go to analysis. I don't know why this menu doesn't want to come down right away. Ooh, analysis. There we go. Confidence intervals. Again, we could do a mean with one sample or a mean with matched pairs. I'm going to do a mean matched pairs first. My confidence level I want is 0.98, and I tell it to use the column 1 data, that's the 2018 fall temperatures, and column 2 data, that's the 2019 fall temperatures, and evaluate. All right, 0.34336 to 18.98997. I think that's different by just one, what would that be, like 10,000th, right? I think the last one had a 7 there at the very end. This has a 6, essentially the exact same thing. So that's one way I could do it. I can also go to analysis, confidence intervals, and do mean one sample. Again, make sure I have the correct 0.98 confidence level, and then tell it my sample size of 9, sample standard deviation of 9.6667, and then standard deviation here. I still have that copied and pasted in, right? Again, that was from the descriptive statistics we looked up for the differences, and evaluate. All right, I get 0.34337 to 18.98997. Either way, it works out, okay? You choose how you want to use StatDisk to make that happen. Okay, so let's conclude. We're almost done here. Let's see. We always conclude with our confidence interval interpretation sentence. We are 98% confident that the interval from 0.34, I'm going to round to 0.34, that sounds good, to 18.99 captures, oh, I should put units in here, degrees Fahrenheit, captures the true mean difference, and here I'm looking back up at the problem statement, the true mean difference in fall temperatures of 28. So in fall temps of 2018 and 2019. There we go. Now, if I were asked if this confidence interval shows convincing evidence that there is a difference, the answer would be yes. 0 is not within this interval. This entire interval is positive. So there is convincing evidence that there is a positive difference between 2018 and 2019 temperatures, or that 2018 has higher fall temperatures than 2019. Okay, so that's it for chapter 9. In the next video, we will start the chapter 10 test review.